Okay, so we talk about Bellman Ford algorithm, which is a general algorithm. So it's not like Dijkstra's algorithm that there is a restriction on the edge weight, because Dijkstra's cannot handle the negative cycle. So for that we had taken the edge weight to be non-negative, but Bellman Ford there is no such restriction. So what are the input? Input is basically a graph, directed graph V comma E, and the edge weight. So this is basically W to R. So here there is no restriction of the non-negative edge. So edge could be negative also. So that means there is a chance of negative cycle. But anyway, Dijkstra's can handle, Bellman Ford can handle that. And there is a source vertex, which is also another input. So this is also a single source shortest path algorithm. So given a source, we are finding the we are finding the shortest path from that source to other vertices. So output would be delta of S comma V, where for all V belongs to this. Either it is exist, otherwise it will be infinity. So otherwise there will be a negative cycle. So you have to report the negative cycle. Okay, so this is the Bellman Ford input output. Otherwise negative cycle will be there. If we have to report that the Bellman Ford should be able to report that, because here there is a chance of negative cycle also. Okay, so let us write the pseudocode for Bellman Ford algorithm. So it is basically the initialization part is same as Dijkstra's algorithm for all vertices. So degree of V to be infinity. Initialization phase is same as Dijkstra's. So this is the initialization, and then what we are doing? We are doing branch of relaxation step. So how many times? For I is equal to 1 to V minus 1 time. Why V minus 1 time? We will come to that. Then for each vertex, sorry, each edge, for each edge we will try to do the relaxation. We check whether do if dV. So we take a vertex U to V. This is a vertex U to V. Sorry, this is the edge U to V. Now this was having a degree. Now we have some where S is there. Now this is a path from U S to V like this. We go from S to U, then U to V. Now if this path is better than this, then we have to relax. So that is the relaxation step. If this path is the S to V, we go to S to U, then U to V. This. Now weight of that path is du plus this. Okay, because du is the distance estimate from S to that vertex. And if that is better than the degree, the distance estimate what we have, then we must relax that H. So that is the relaxation step we must do. Okay, so if du is greater than, sorry, if dv or if du plus delta uv is less than dv, then we must relax this, then dv must be relaxed. Okay, so this is the 5, 6, 7. So this is the relaxation step. So we are relaxing this vertex V. So this is the direct edge U to V. So this is dV. Now if this dV is greater than this new path, we come from S to U, then this direct edge, then we must relax this edge. So, this is called, this is the relaxation. And this we are doing how many times? This we are doing for this we are doing for all edges. So, this is the inner loop, and outer loop how many times? V minus 1 time. Why V minus 1 time? We will come to the correctness of this algorithm. So, there we will see why it is V minus 1 times. So, anyway, this is the outer loop. This outer loop is we are running from, if V is n minus 1 times, order of n times, and the inner loop we are running from for each of these vertices, for each of these edges. So, somehow we need to maintain the edge numbering, so that we can just, we will come to an example of Bellman Ford how it is executed. So, now this is the step. Now, we have done, so after this step we have done enum number of relaxation. So, now still if we could further relax the edge, then there is a chance, then there is some indication that that there will be a negative cycle. So, that step we have to follow. Otherwise, after this, after completion of 7, if there is no negative cycle, then it must converge. The delta, the d of this must converge to a delta of S comma V. But if after doing, this is so many relaxation we are doing, this is V times E times. So, order of V into E times relaxation we are doing. So, even doing so much relaxation, if even though we can reduce the degree further, that means even after this step, if we can relax a vertex further, then we must say that there is a negative cycle. So, it will never converge. So, it will keep on decrease. If there is a negative cycle, that means it will keep on. So, that step we have to follow. So, this is the last step for each vertex. Last time, if it is there is no negative cycle, then there is no meaning of this step, but anyway we have to have this step to, in order to have this checking of negative cycle. Now, for each vertex, this is last time, do if this is the final checking. So, dV, so if the du is du plus wuv is less than dV, that means dV is a candidate for relaxation V. So, that means there is a negative cycle, that is why it making this that is it is not converging, then report negative cycle, report negative cycle. Okay. That is it. So, this is the pseudocode for Bellman Ford algorithm. We just report the negative cycle, because we have done enough relaxation. After that, we just, this is for the check of negative cycle, checking of negative cycle. After that, we will just try once more time for the edge wise. Now, then if we see the vertex is further could be can be relaxed, then that means it will never converge, again it will further can be relaxed like this. So, that means there is a negative cycle, and in the correctness we will see why we are doing this loop for V minus 1 times. So, that we will see in the correctness of this theorem. Okay, now, before going to the example, let us talk about time complexity of this theorem. What is the time complexity? So, analysis is time analysis. So, this initialization step is basically same, order of V, this is basically yes order of V. Now, this loop is basically V times and this loop is E times. So, this is basically order of V comma E. So, that is the time for, this is the time for Bellman Ford algorithm, order of V times E. Okay. So now let us take an example how this algorithm is working. So let us take a graph, then we will execute this Bellman Ford on that graph. Okay, so example of Bellman Ford. Okay, so and at the end Bellman Ford should give us delta of V is basically dV is basically delta of S comma V at the end of Bellman Ford. Otherwise, it should report the negative cycle. Okay. So this is at the end of Bellman Ford, it should give us this. Anyway, let us take an example. So let us take a graph, directed graph A, B, C, D, E. So let us have the edges. So this is here, this is here, this is here, this is here. Okay. So let us have this weight. So -1. So here we are allowing the negative weight because it can handle the negative cycle. 5, 2, 2, say -3. So -1, 4, 3, then 5, 1, 2, -3, 2. Okay. So this is the input of the Bellman Ford algorithm. Now we take a source vertex. Suppose S is our source vertex A. Now we put everything into the A, B, C, D, E. So this is degree we are assigning 0 and each is infinity. So this is the initialization step. So source vertex has degree 0 and each are infinity. Now we have to run this for we have a outer loop from I is equal to 1 to V minus 1 times, and in inner loop we have to run it for how many times? For all each edges. So somehow if we can have a edge numbering, it will help us. So let us numbering the edges. This is number 1 edge, say this numbering is not unique. You can have your own numbering and you can follow this numbering in each iteration. Okay. This is number 3, maybe this is number 4, this is number 5, this is number 6, this is number 7, and this is number 8 edge. Okay, we are just numbering this edge in order to do it for all the edges, because if you recall the pseudocode, for all I you have to do it for all the edges. Okay, now for I is equal to 1, we have to do it for all the vertex. So we start with, so we initialize the degree, this is 0, this all are infinity except this. Okay. Now we start with this edge, this is U, this is V. Now both are infinity, so no relaxation is possible. So there is nothing is changed there for edge number 1. Edge number 2 also, this is infinity, this is infinity. So there is no relaxation is possible for this vertex. Edge number 3, same, no relaxation. Edge number 4 is this. Now for edge number 4, this is U, this is V. Now dV is infinity. Now we have a path which is du 0 plus -1. So this is -1. So this is U, this is V. So this was infinity. Now we have somewhere S is there. So this is a direct path. So this is minus 1. So this is degree is 0. So this minus 1. So this must relax because we have a better path. So this h must relax to minus 1. So this must relax to minus 1. So which is b? B must relax to minus 1. Okay. So now, so this is h number 4. Now h number 5 also similarly, this must relax to 4. So this is C. So this must relax to 4, and then 5, then 6. 6. Now if you look at 6, this is U, this is V. So U V. This is U, this is V. Now the degree of this is basically degree of this is V 4. Now degree of U is what? Degree of U is basically minus 1, and we have a direct part with 3. Okay, so S is somewhere here. So that means we have a path from S to this node with minus 1, then we can take this direct path. So that is a new path from S to V with a cost minus 1 plus 3. It is basically plus 2, which is better than 4. So we must relax this. So we must relax this to be this 4 to be 2. Okay, because that is the better path. So this is basically C is now became 2. Okay, so this is the relaxation we are doing. So this is H number 6. Now H number 7. H number 7, this is infinity. So this will be no change. H number 8 also no change, because this is infinity, this is infinity, there is no change. Okay, so edge number 8, so all edge exhaust. So this is for I is equal to 1. This is for I is equal to 1. Now for I is equal to 2, if you remember, the outer loop is for I is equal to 1 to V minus 1. I mean number of edge minus 1, number of vertex minus 1. So now I is equal to 2. I is equal to 2 will do, we have to again do the inner loop for all the edges. Now since we have already have a edge numbering, we can follow this numbering or we can have a different numbering, but we have to make sure that we have visited or we have checked this for all the edges, that inner loop is for all the edges. So but if we do the numbering, and we can, if you follow the numbering, it will simplify, I mean there will be a simplicity in this algorithm. Okay, so we are basically following the same numbering, but it is not required to follow the same numbering for the next loop. We can have a different numbering also. Only thing we have to ensure that we are doing this for each edges. So that we have to ensure. Okay, so if we do this for I is equal to 2, we are following same thing. So we start with this vertex. Sorry, this H, this is U, this is V, this is U, this is V. Now this is having degree infinity. Now we have a new path which is basically from S to V U, we can go minus 1, then we can take this 2, which is basically minus 1 plus 2, 1, which is better than infinity. So this will be now 1. So basically E is now became 1. Okay, E is now 1. So now H number 2 is this one, this is U, this is V, again this is minus 1, this is plus 2, so this will again become 1. So D will become 1. Okay, so this is edge number 2. Edge number 3 is this one. So now this is 1. So that means there is a path from S to this node. This is U, this is V now. So there is a path from S to this node with a cost 1, and we have a direct edge with a cost 2. So that means now we have a path from S to this node with a cost 1 plus 1, which is basically 2. But we already have a path which is minus 1, which is not better. So we don't have to relax this. This node is not getting relaxed because the path which we already have degree is better than the path which is currently we have. So we are not relaxing that. So come to 4. So this is edge number 3, edge number 4. If you come to edge number 4, this no change. Edge number 5. edge number 5 is here. So this is 2, this is 4, so no change, no relaxation is possible, no relaxation, because this is better path we have. Now edge number 6, edge number 6 is this one. So this is basically what? This is u, this is v for this edge 6. Now this is du is minus 1. Then if we take this path 3, so this is minus 1 plus 3, 2. So we have a path 2 to from S to this node, and but we have a already path 2, so there is no change. Okay, so no, we are not relaxing this edge. So edge number 7, edge number 7, this is u, this is v. So this is u means, so this is the degree of u. So that means we have a path from S to u with a cost 1, and then we can take this direct edge with a cost 5. So that will give us a path from S to this node with a cost 1 plus 5, 6, but which is not better than 2. So we are not relaxing this vertex v. So then edge number 8, for edge number 8, this is u, this is v. So we have to check whether we can relax this v. So the degree of v is now what? Degree of v is 1. Now what is the degree of u? Degree of u is basically 1. So that means we have a path from S to this with a cost 1. Then what is the direct edge? It is minus 3. So then so now we have a path from S to this. By this we take this du 1, then we take the direct edge minus 3. So this is basically 1 minus 3, so plus minus 2. So minus 2 is better than this, so we must relax this. So this will be now minus 2. So v is relaxed. So d is now minus 2. Okay. So this is edge number 8. So this is for I is equal to 2. Now for I is equal to 3 we need to do, because this vertex, how many vertexes? 1, 2, 3, 4, 5. So 5 vertexes means, so the outer loop is v minus 1 times. So that means 5 minus 1, at least 4 times we have to do this. Now if I is equal, so I is equal to 4 we have to do. So for I is equal to 3 we can just do it again. So again we have to execute the inner loop for all the edges. So we have to just check all the edges, and we have to see whether we can relax the vertex from. So edge means u to v. So you have to check whether the v vertex could be relaxed. Okay. So now we start with the, we can follow the same edge numbering, or you can have a different edge numbering, doesn't matter. So since we already have a numbering, we can just, for the simplicity, we can just follow the same numbering. Okay. So we start with this edge number 1. So if you start with edge number 1, this is u, this is v. Now this is minus 1, this is 2, so this is plus 1. So no change, same. So no further relaxation is needed for this vertex v. Now edge number 2, this is u, this is v. So this is basically minus 1 and plus 2. So this is basically plus 1. So this is already having minus 1. So plus 1 is not better than minus 2. So no relaxation is required for this vertex. Okay. So edge number 3. Edge number 3 is this one. This is u. This is v. So this is minus 2 plus 1. So it will be minus 1. So it is same as which is the same the degree which is having. So there is no relaxation is needed for this vertex. Now number 4. Number 4 is this one. So this is basically minus 1, which is same. So no relaxation is required for this vertex v. So number 5. Number 5 is this one. So this is 0 plus 4 is 4, which is not good as 2. So no relaxation is required for this vertex. Then 6. Number 6 vertex is this one. So this is minus 1. So minus 1 plus 3 is 2. So this is already same as the this. So there is no further relaxation is required for this vertex v. Then number 7 is this one. So minus 2 plus 5. So, 3. So, 3 is not good as 3 is not better than 2. So, there is no further relaxation is required for this vertex V. So, number 8 is basically this one V uv. So, this is minus, this is 1, this is minus 3. So, minus 2. So, which is same as this. So, no further relaxation is required. Okay. So, this is converging. So, this converges. So, these become converge. So, there is no further changing happening for I if we just have another loop. So, this is converging with the this degree is converging with the delta. So, delta of V is now become S of S comma V. So, these are basically the weight. So, these are basically our deltas. These are basically our deltas. So, that is basically converging, because there is no negative cycle in this graph. If there is a negative cycle, I will suggest you to do an example in the home. So, you just put a negative cycle here, maybe some so this is a maybe you take this one, okay, this and this. Okay. So, try to put a negative cycle over here, just put a minus 2 over here, then there is a negative cycle, then try to execute this, then it will not converge. You can just verify this, it will not converge, it will keep on relaxing the edge, keep on relaxing the vertices over in this region. So, it will not converge like this. So, if it is converging, that is why we have a final check, and also in the correctness we will discuss why this outer loop is for V minus 1 time. Okay. So, this we will discuss in the next class. Thank you.